So this spring does not obey Hooke's law. When the spring is stretched downward a distance x, the spring exerts an upward force of magnitude alpha x squared, where alpha is a positive constant. Initially, the spring is relaxed. A block of mass m is attached, and it falls. It falls, and as the spring stretches. And in terms of given variables, derive an equation for the speed of the block after falling a distance x1, so maybe like after falling a certain distance, how fast it's moving, the power the spring exerts at that point, and then the maximum distance the block stretches. The maximum distance the block falls, so we'll call that x2. And I drew a little picture of a police officer, you broke Hooke's law. And I mean, Hooke's law is not really like a law in the universe that says every spring must confine to the famous, equation F equals negative kx, right? It's not like that's a very idealized model. In most scenarios, they actually follow some other sort of proportionality where the force is maybe proportional to x squared. So how are we going to solve these problems, right? Because we're so used to 1/2 kx squared, and we're going to see, does 1/2 kx squared work? What do we have to do to solve these problems? And we're just going to get right into it. We want to find the speed of the block after falling a distance x1. When we think of speed, springs, and falling a certain height, you probably think of energy, and that's exactly what we're really going to do. We know during this entire time energy is conserved, so E initial equals E final. Please start every derivation with that. We're going to have, so it's going to fall a distance x1. So initially, so at point A, before it starts falling, it's going to have some UG, right? It's going to have some potential energy relative to x1, so whatever that height is. So we're going to say it's going to have some UG, right? And then the spring is not stretched, so there's no energy stored in the spring, and it's not moving, so there's no kinetic energy. Afterwards, relative to x1, so relative to that height, we're going to say there's no UG. Remember, UG is mgh. We can set the height, where h is equal to 0, we can set that to wherever we want. So I'm going to say h is 0 at x1. Maybe we'll say that's right there, x1. So relative to x1, no UG, but the spring is now stretched, right? It's going to be stretched a certain amount, and it's also going to be moving. So we're going to have some energy stored in the spring plus some kinetic energy. Now, from here, now we can just plug in everything we know. We have mgh equals, and now, you might be tempted here, use spring, let's just put in 1/2 kx squared. The reason we can't do that is because we know that the force exerted by a spring to cause a potential energy 1/2 kx squared, it's going to be the integral. So actually, I'm phrasing my thoughts a little bit wrong here. We know that the work done by conservative force is equal to negative u. All right. Okay. So in other words, so the work done by conservative force equals negative u. Negative work is equal to the potential energy, which means negative f of x dx equals u. Well, the force exerted by a spring is actually I'm doing this kind of wrong. It would kind of be negative the integral of the force by the spring, which is going to be negative f of x dx, right? So in order to get f of x dx, if we integrate this, we would get 1/2 kx squared equals u. In other words, what I'm trying to say here is that the reason u spring is equal to 1/2 kx squared is because the spring we're dealing with obeys Hooke's law. In this case, instead of doing u spring, you would have to do energy. You would have to do, energy. Really just energy. So if we were to, we're doing energy either way. What am I saying? We got to use work. We can't really use potential energy. You could integrate, work and potential energy, because it's a conservative force, they are linked. But work just, we can use the work energy theorem. We can say, okay, UG, there's initially some UG. Instead of having U spring at the end, we could just say that during, at U initial, there's going to be, or energy initial, there's going to be UG minus the energy removed by the spring. The spring is going to do negative work, right? Because it's in the opposite direction of the movement. So we'll say UG minus the energy removed is going to equal the kinetic energy. So UG is going to equal mgh minus, now for the work done, it's going to be the integral of alpha x squared. Now, what are the bounds going to be for this integral? Well, initially there's no stretch, and then eventually it's going to go to x1. So we're going to say the upper bound is x1, and then the initial bound is 0, right? There's no stretch initially. So, and then k is equal to 1/2 mv squared, which is obviously what we're solving for. Or v is obviously what we're solving for here. So mgh minus, alright, let's integrate this. So if we think about reverse power rule, right, we're going to have let me think about this, 1/3 alpha x to the third, right? Because then when you do your power rule, you put the 3 here, 3 times 1/3 is just 1, you do -1, you get alpha x squared, which is consistent with everything we've been doing here. So we're going to say 1/3 alpha x squared. And we're doing it from x1 to 0, so it would technically be like x1 squared, minus 1/2 alpha, 1/3 alpha 0 squared, right, because of our bounds, but this is going to be 0 either way, so we're not subtracting anything. So I can just kind of get rid of that whole thing. So the third is equal to 1/2 mv squared. So now I can multiply everything by 2. Divide everything by m. So I'm going to get kind of this going on here. Okay, I'm writing way too close here. So you can fast forward if this is taking too much time. And then we're left with the v squared. So we take the square root, and you get this expression. Not v squared, just v. So this would be kind of our answer for A. So yeah, the power the spring exerts at x1, well, for power, remember, it's just going to be work over time. So power is going to equal the amount of work, your change in energy over time. So power is going to equal, well, we have a 1/3 alpha x. This we already solved for the work done. It's right here. So we could just say alpha x1 to the third over 3t. Wait a second, we don't know time. Time is not a given variable. Okay, so this is obviously not going to work. The other equation for power is force times velocity. So instead of doing this equation, we can just say power is equal to force times velocity. And then that becomes a lot more simple because we actually solve for the speed or the velocity. And then we would just multiply it by the force at that time, which, hey, they already gave it to us. Thank God, right? So power is going to equal force, which is alpha x squared, times the velocity, which is just this whole thing that we kind of solved for here. So that is the rate at which the spring is kind of converting energy and doing work. The rate at which it does work, essentially. The maximum distance to which the block falls. Now you might be tempted, okay, things at rest, they have no net force. So if it's at the maximum distance, the alpha is going to equal, or why am I saying alpha? Alpha x squared is going to equal mg. The upward force is going to equal the downward force. Remember, no net force means constant velocity. Right now, there is no, like when we attach it, there's a net force downward because there's no upward force by the spring. There's only an upward or downward force, gravity. Eventually, it's going to stretch. So as it's falling, there's going to be a point, a certain distance, where the forces are equal. But by that point, it's still falling, right? Because there was a downward force, net downward force here. So as it falls, even when the forces are equal, that just means constant velocity. It's going to still stretch down further than that. And that's what we're solving for, that ultimate maximum distance that is going to fall and stretch, and then it's going to go upward again. So what is that distance? Well, what we would do is we would, once again, another energy statement where energy is conserved. E initial equals E final. In this case, the energy initial is going to be UG. And the spring is going to remove energy from the system. And we're going to say UG relative to that final distance, whatever that final distance is, x2. So relative to x2, there's going to be some UG, and the spring is going to remove energy. So we're going to say minus the work done by the spring is going to equal. Well, at the end, it's going to have no energy. There's no UG, and it's not moving. The spring will have removed all the energy. So we're going to say 0. From there, it just becomes a case of, okay, mgh minus, and then we're going to do that same integral 0 to x2 this time, of alpha x squared dx is going to equal 0. Or I'm going to kind of kneel down for this because it's getting high. I don't want to make it too slanted. We'll say mgh is going to equal minus 1/3 alpha. I'm making little mistakes here. Alpha x to the cubed is going to equal 0, and then we can solve for x2. Just doing some algebra from here. So you get a cube root. You're going to have 3 mgh over alpha is going to equal x2. And there you go. Oh, and wait. H is just x2, right? Because the height it falls is x2. What's going to happen then is we have an x2 here, and we have an x2 here. So we can kind of get rid of one of those x2's. Don't do that in algebra class. So we have mg is equal to x2 squared, and it's a very similar thing. We would just drop this h right here, because there was no h to begin with. So you do times 3 divided by alpha, take the square root, and you get your answer. So I'm going to kind of box everything here. And yeah, that was how you solve basically an energy problem. It's just more fun when we do things a little bit different.